So let's take a look at solving improper integrals. So looking at number 1, we have the integral from 0 to infinity of 1 over 1 plus x squared dx. And whenever you have an improper integral, especially when one of the bounds is infinity itself, it's probably a good idea to set up a limit, because normally in functions, when you plug in infinity, you don't really get a definitive answer. But what you can do is find the limit of it. So I'm actually going to replace infinity with b as my upper bound, and I'm going to add the limit notation. So I'll get the limit as b approaches infinity. So all I did is replace the upper bound with b. So instead of saying infinity, I'll put like so. So for the integral from 0 to b of 1 over 1 plus x squared dx. So now when I integrate 1 over 1 plus x squared, this one's pretty easy because the integral is just arctangent of x. So I'm going to rewrite the limit. So I get arctangent of x. Now I can add my bounds. So we're going from 0 to b. And when I evaluate my bounds, I get the limit as b approaches infinity of when I plug in the top bound for x, and then when I plug in the bottom bound for x. So I get arctangent of b minus arctangent of 0. Arctangent of 0 is obviously 0, so that's out. And all we're left with is the arctangent of b. So now I can directly substitute infinity in for b, and we get arctangent of infinity. And arctangent of infinity, or the limit as arctangent function goes to infinity, is actually going to be equal to pi over 2. So for number 2, we have the integral from 2 to infinity of x over the cube root of x squared minus 2. And once again, because there is an infinity here as one of my bounds, I'll set up limit notation. And I'll replace infinity with a variable, so I'll just call it b. Limit as b approaches infinity of the integral from 2 to b of x over the cube root of x squared minus 2 dx. So in order to evaluate this integral, obviously we can just use u substitution. So I'll step away from the limit for a second and just evaluate the integral. So I can make u equal to x squared minus 2, which means du, or the derivative of x squared minus 2, is just going to be 2x dx. And dx will then equal du over 2x. When I plug that in, I get the integral of x over the cube root of u, because that's what I did for u substitution, times dx, which is equal to du over 2x. The x's will cancel, and I can actually change this to u to the 1/3 power. So I get the integral of 1 over u to the 1/3 du. And I can use the power rule, but first I gotta move the u up, so u to the negative 1/3. So now I add the power by 1 and divide by the same power. So negative 1/3 plus 1, or negative 1/3 plus 3 over 3, it's going to be 2/3. Divided by 2/3 is the same thing as multiplying by 3/2, and the du goes away. So the integral will be 3 over 2 times u, which is x squared minus 2, to the 2/3 power. And I can put it in my bracket and insert the bounds, which go from 2 to b. So in order to evaluate this, I can just isolate the 3/2 and keep it outside. So I get 3/2, and I put it in the bracket. Now I can evaluate what happens when I plug in b and when I plug in 2. So when I plug in b, I get b squared minus 2 to the 2/3 power minus what I get when I plug in 2. 2 squared is 4, 4 minus 2 is 2, and 2 to the 2/3 power will be the cube root of 4. So now I can put my limit definition back in, because we said the limit as b approaches infinity. So if I rewrite this, the limit as b approaches infinity of 3/2 times b squared minus 2 to the 2/3 minus the cube root of 4. Now if I substitute infinity in for b, then I'll get 3/2 times infinity squared minus 2 to the 2/3 power minus the cube root of 4. Now if I evaluate this inside here, I'll still get 3/2 on the outside. Infinity squared is infinity, and infinity minus 2 is still infinity. And infinity to the 2/3 power is obviously still going to be infinity. We get infinity minus the cube root of 4. The cube root of 4 is insignificant compared to infinity, so we'll just get 3/2 times infinity. And 3/2 is also insignificant, so the limit is infinity. Or in other words, it will diverge.